Hello, I'm Professor John Kelly, and this is the Weber Auto YouTube channel. In this video, we are going to learn about the heat pump systems used in Tesla vehicles. Now, if you are in the market for an electric vehicle, and you live in an area where the outside temperatures drop below 10 degrees Celsius or 50 degrees Fahrenheit, you really should pay attention to the type of cabin heating system that electric vehicle has, because it can and will affect your driving range if you want the heat turned on inside of your cabin. So there are three different types of cabin heating systems that I'm going to show you that are still used today in new battery electric vehicles. So the very first one I'm going to show you is an old school, really shouldn't be used anymore, cabin heating system. Let's go look at it. Okay, on this cart I have put together the old school cabin heating system. It includes what's called a heater core. And the heater core has been around for, I don't know, I forgot to look up when it first started, but I suspect 100 years. It is basically a little mini radiator that we pump hot coolant through, antifreeze through, inside of your passenger compartment. Your blower motor blows air through it, and the heat transfers from the coolant into the air and warms the passenger compartment. The source of the heat came from the internal combustion engine. But since electric vehicles don't have internal combustion engines, somebody decided to invent an electric coolant heater instead. So this part right here is the high voltage cabin coolant heater. And when you turn the heat up all the way, this thing can draw 7,500 watts or 7.5 kilowatts. Now we have a coolant reservoir right here that we can use to add coolant to the system. And then down below the reservoir, we have a pump, an electric pump. So we put coolant in the reservoir. It goes down to the pump through the hose, comes up through the pump hose to the heater, goes from the electric heater through a hose over to our old school heater core, through the heater core and back to the coolant reservoir. So we basically just replaced the internal combustion engine heat source with an electric heat source. 7,500 watts on high. Now if you want your windshield defogged or defrosted on a cold morning, then the air conditioning compressor has to turn on, and it can draw upwards of 2,000 more watts. On a cold day, if you drove with your heat on high and the air conditioning compressor was running for defrost purposes, dehumidification of the cabin air, you would be using 9,500 watts or 9.5 kilowatts. If you drove for 1 hour like that, that's 9.5 kilowatt hours. And if you could drive 4 miles per kilowatt hour, then that would be 38 miles of range lost because of the energy used by these high voltage components. Now, if you count all the parts involved in this old-fashioned cabin heating system that are here on this bench, the hoses, the parts, there are 11 pieces. And what some manufacturers have done, and this takes us to the second type of cabin heating system, is they have gone to an electric air heater. So this part right here is called a positive temperature coefficient PTC air heater. It has an orange cable. It connects to high voltage, and there's a controller built into the bottom housing here, and then we have these heat fins, and the controller electrically heats these fins, and the blower motor blows air through it, and we get hot air inside the passenger compartment of an electric vehicle. This one piece replaces all 11 of these other pieces. So there's fewer parts, there's virtually no maintenance on this electric air heater. On these ones that still have coolant running through a heater core, you will still have cooling system services at so many years or miles. So this PTC air heater is a nice way to go as far as reduction of parts. However, it still can draw almost exactly the same amount of electrical power as the PTC coolant heater that we have right here. So we have a PTC coolant heater, we have a PTC air heater. They both use a lot of power. The big difference is the PTC air heater only has one part. one piece instead of the 11. So there are vehicles out there that have a heater core. There are vehicles out there that have a PTC air heater. And now let's look at the third method of heating a passenger compartment, and that is with a heat pump. There are several vehicle manufacturers that use heat pumps in their vehicles. They are not all the same. The heat pump we are going to look at today is used in Tesla vehicles. Now I have two Teslas right here behind me. I have a Tesla Model Y right here, and I have a Tesla Model 3, the purple one back there. That Model 3 was made in 2018, and it uses the PTC air heater for the passenger compartment heat. And all the way up through late 2020, Tesla still used the PTC air heater in the Model S, X, and 3. But in late 2020, they switched everything over to a heat pump. And the heat pump system that Tesla uses is quite remarkable, and we're going to explore that today. But they are not the only ones with a heat pump. General Motors way back with the EV1 electric vehicle had a heat pump. A Nissan Leaf has had a heat pump since 2013. There are other vehicles that have heat pumps. I have a Kia Niro electric vehicle here in the shop that has a heat pump. I have a Subaru Crosstrek plug-in hybrid that has a heat pump. There's several Toyotas that have heat pumps. There's differences between those heat pumps as far as their efficiency and what temperature ranges they will operate. And so let's take a look at this Tesla heat pump system. The first thing you may want to know is, does your Tesla have a heat pump? So to find out, if you'll get into your Tesla, touch the car icon in the bottom left corner, and then select Software from the menu, and then select Additional Vehicle Information. Look down to where it says Cabin Heater. If it says Resistive is your cabin heater type, then you have the PTC air heater. If it says Heat Pump, then you have the heat pump that we are going to talk about in the rest of this video. The advantage of a heat pump is that it can be very efficient as far as the use of electrical power. So most heat pump systems, regardless of the brand, use the electric air conditioning system compressor as part of the heat pump system. And that is the only device under normal temperature operating conditions that uses electrical power. And it typically only uses between 1,000 watts and maybe 2,500 to 3,000 watts of electrical power. And by comparison to the 7,500 watts of the PTC air heater and the PTC coolant heaters that we just looked at, this is quite a savings in energy usage, which means you will be able to drive farther down the road on your existing battery power with a heat pump as compared to the other methods of heating the cabin that we looked at. Now, Tesla heat pumps are not rated by their efficiency. Instead, they are rated by a coefficient of performance. And the reason for that is it is possible to get more heat energy transferred into the passenger compartment than the electrical energy used to run the air conditioning compressor. So that would be more than 100% efficiency, which is not possible. So Tesla uses what's called a coefficient of performance. If all we get is heat energy that equals the electrical energy put into the air conditioning compressor, then the coefficient of performance is a 1.0. If we get more output in the passenger compartment, more heat energy output than we used in running the air conditioning compressor, then we get a COP value higher than 1. And on Teslas, according to their service information, their COP can be as high as 5.6, which is very impressive. The COP calculation is simply a ratio of the output energy divided by the input energy. Now, Tesla's heat pump system has up to 30 different modes of operation, and I'm not going to take you through all 30 modes. This video would be extremely long. But I will show you where it gets its heat and how it transfers it into the passenger compartment or the cabin, as we've been calling it. When the high voltage battery temperature is above 10 degrees Celsius or 50 degrees Fahrenheit, we can transfer heat energy from up to 16 different sources on the vehicle into the passenger compartment, which is quite impressive. And of course the battery is one of those. Okay, so right here I have a 2022 Tesla Model Y Performance vehicle, and I've removed the luggage compartment and all the trim panels from under the frunk lid here. And looking inside of here, we have the air conditioning compressor and a supermanifold and the radiator and some hoses and pipes and other things. These are just parts of the heat pump. This is not the heat pump. The heat pump consists of all of these different pieces on the vehicle that create heat energy, including the front and rear drive units, the electric motors, the entire high voltage battery, the radiator, the hoses, pipes, valves, pumps. There's all kinds of parts involved in the heat pump system. So there is no part called the heat pump. So the heat pump system is intertwined throughout the entire vehicle. So let's get started by looking at the individual components involved in the heat pump system. Okay, the first part of the heat pump system I want to show you is actually inside of the cabin of this vehicle. And to understand where it is, if you look here under the frunk, we have 5 pipes, 5 aluminum pipes going into the cabin, the passenger compartment on this vehicle. Those pipes play an important role in the heat pump system. So I have built most of the heat pump system on a workbench over here. Let's go take a look at where those pipes go. Okay, the 5 pipes that we just looked at underneath the frunk lid of that Model Y are right here. And 3 of the pipes are for heating the cabin. 2 of them are for cooling the cabin. So let's follow these pipes down. The 3 pipes that are used for heating go to a special part called the cabin condenser. And there's a driver's side and a passenger side of the condenser, so you can have individual heating controls. So there's a cabin driver's side inlet and a passenger side inlet of hot refrigerant from your air conditioning system. And then there's a single outlet where they both return. Now, what else do we have here? We have a blower motor that's going to blow air through your cabin filters that are right here. And they are in front of the part that is used for cooling your cabin, which is called the evaporator. And it has the other 2 pipes that are here in this 5-pipe pentaport connection there. But when we are heating the cabin, we can run just the cabin condenser to allow air to be blown through it and transfer heat energy from the hot refrigerant into the air. We are also running the air conditioning compressor. We can run a little bit of refrigerant through the evaporator, which gets it cold, which will cause any moisture in the air to condense on the outside of the evaporator and drip out the bottom of the car. And that's for dehumidification of the air while heating, so that the inside of your windshield doesn't get all frosted up or even frozen on the inside in some cases. So all of the other parts that are involved in the heat pump system operating are there so that we can get heat energy into the refrigerant and pumped inside the cabin here to this inside condenser. Everything that's part of the heat pump system is dedicated to getting heat energy to this inside condenser. So the cabin condenser is the source of heat that air is blown through to heat the cabin. Now, another source of heat energy can be from the blower motor itself. This is a 3-phase 12 volt to 16 volt, depending on your low voltage system voltage, blower motor controlled by the front vehicle controller. And I've taken the clip out of it so I can remove the blades here. If I take the fan blades off and we look at the back side of it here, we have permanent magnets. right here, and then over here we have the stator coils. Those stator coils can get hot and produce heat as part of normal operation of the blower motor. And so on the back of the blower motor, if you look real carefully down in the edges here, it has a special set of fins, kind of a spiral set of fins on the other side of this that help pull air through the stator and that to help cool the stator. But that air transfers heat energy from the stator into the air, and then that comes into the cabin and helps heat the cabin air also. So although that is a minor source of heat, it is a source of heat. All right, now the third source of heat might be surprising to you, and it's actually up in front of the vehicle, and it's the vehicle radiator. So let's take a look at it here on my bench. All right, on my workbench right here, I have the whole radiator assembly, and I've unclipped this upper cover that has the active shutter in it that can close and block airflow from coming in, and of course it can open and allow airflow under certain situations. There's a little motor that controls that right there. But let me get that out of the way so that we can see the radiator. Right here is the radiator. And you might be thinking, big deal, radiator. Every car has a radiator. Well, this is a special radiator. This is a pretty big radiator compared to some other electric vehicles. And one unique thing about this radiator is that we have the fan motor below it. You can't see it here, but the fan motor is below it here. And that fan motor can pull in what we call ambient air. So we're just going to pull air through the radiator, not for the purpose of cooling anything, but for the purpose of transferring the heat energy that's in the air right here that we're breathing through the radiator, transferring that heat energy into the coolant of the radiator, and then that heat energy from the coolant eventually works its way into the refrigerant and into our cabin condenser. So on this radiator, the fan can be blowing at high speed, and you'll put your hand near it and it's cold air. It feels cold to us, but there's still heat energy in cold air. And so we can take, this is free energy, it's just in the air itself. We take that free energy and put it into the coolant that goes through the radiator. Now, of course, this radiator can act like any other radiator on any other vehicle, and that is if it's a hot day and we want to get rid of some heat energy, then we can pump hot coolant through the radiator, turn the fan on, and transfer the heat energy from the coolant into the air. So one more time, this radiator can transfer heat energy from the air and put it into the coolant, or it can transfer heat energy from the coolant into the air, depending on the situation, whether something's too hot or something's too cold. All right, so that is our third source of heat energy on this vehicle. Okay, our fourth source of heat energy is the high voltage battery. And if you look at this photo of the high voltage battery underneath our Model Y right here, you can see that it is very large and it fills up almost the entire underneath of this Model Y. But in this photo here, you can see there are 4 coolant hose inlets at the front of the battery, and there are 4 hose inlets at the back I'm not showing you. But we have coolant that runs through this battery. And the coolant going through the battery can allow heat energy that's stored in the battery, the hardware itself, the physical parts of the battery, to transfer into the coolant. Or if we need to heat the battery, we can transfer heat energy from the coolant into the battery hardware itself. So it can go both directions also, the heat energy at the high voltage battery. So that is our fourth heat source. Our fifth and sixth heat source are built into one big component that you can see here in this photograph called the power conversion system, or the PCS. Now on the passenger side of the power conversion system is a high voltage part called the DC to DC converter. And the job of the DC to DC converter is to take high voltage from our high voltage battery and step it down to a low voltage so that we can run the rest of the vehicle either on the 12 volt system or the 16 volt system that Tesla has. To do that conversion, it produces heat. And so we can transfer heat energy from the DC to DC converter into the cooling passages into the coolant that runs through the cooling plate at the bottom of the DC to DC converter. On the driver's side of the power conversion system is the onboard charger, the OBC. And the onboard charger is never used while you're driving, and so it does not produce heat while you're driving. However, when you are charging your vehicle with an AC level 1 or an AC level 2 charge cord, that charge cord is AC voltage and the battery is DC. And so we have to convert AC to DC, and we have to step the voltage up from whatever the wall voltage is up to whatever the high voltage battery voltage is, typically 400. So if you are using an AC level 1 charge cord, that's typically around 120 volts. We need to charge a 400 volt battery with that, so we have to step up the voltage to 400 and convert it to DC. If you're using an AC level 2 charge cord, those are typically around 240 volts. But we still have to step up that voltage to 400 volts and convert it to DC. That conversion creates heat, and that heat energy is transferred into the coolant that eventually gets transferred into the refrigerant and then works its way into the cabin condenser to heat the passenger compartment. So those were our fifth and sixth sources of heat on a Tesla vehicle. So the seventh source of heat might surprise you. There is a liquid-cooled computer on this car called the Autopilot computer, and it's just over my shoulder. I'm going to zoom in on it. Those two hoses that go through the bulkhead into the passenger compartment have coolant going through those, and that goes into the Autopilot computer. And the Autopilot computer is the one that watches all of the cameras and is used in sentry mode. It's also used when you are driving down the road. And it generates a lot of heat while doing that. So this is a liquid-cooled computer inside the vehicle. Okay, if we look under the frunk lid one more time, right here in the front, we have over here on the driver's side, the air conditioning compressor. And right next to that, we have what's called the supermanifold. And the supermanifold has many parts on it that we will discuss later. But one of the parts that we're going to discuss is kind of hidden down below there, and it is called the chiller. Okay, so those same two parts we just looked at under the hood are right here. Here's our air conditioning compressor. Here is our supermanifold with a whole bunch of other parts involved with it. If we look at the supermanifold itself, here is the supermanifold as far as the refrigerant handling side of the supermanifold. So any refrigerant routing that needs to go anywhere goes through this supermanifold. And we'll talk more about that later. But there's a piece bolted to the supermanifold right here called the chiller. And so here is the chiller right here. And the job of the chiller is to transfer heat energy from the coolant into the refrigerant. So we have coolant inlet and outlet over here on the back side, and then refrigerant inlet and outlet. And this plugs right into the supermanifold right there, and for the refrigerant. So we were just talking about the radiator and how we could transfer heat energy from the air into the coolant, and then somehow the heat energy transferred from the coolant into the refrigerant. This is how. We have that coolant come into the chiller. This is just a heat exchanger. And then that heat energy gets transferred into the refrigerant that also goes through here. And so that allows the heat energy into the refrigerant that then works its way into the cabin condenser to provide heat for the passenger compartment. This is another source of heat. Although it doesn't produce heat, it allows heat transfer. And so I consider that a critical part of the heat pump system. Okay, the 9th and 10th sources of heat in the Tesla heat pump system are the front drive unit inverter and the rear drive unit inverter. So right here on the wall behind me, I have the front inverter right up there and the rear inverter right here. And on the rear inverter, let me zoom in. I've removed the cover. This is the cover right here for the coolant passages for the rear inverter. And you see all those little pins in there. Coolant is going to come in on one of these hoses, go through all those little pins, transfer heat energy out of the high voltage electronics, and have the coolant come out the other pipe there. The heat energy comes from all your high voltage transistors and electronics involved in running the 3-phase motors in the drive units. So heat sources 9 and 10 are the front and rear inverters. Not every vehicle has a front inverter if it's rear-wheel drive. The plaid versions of the Tesla Model S and X will have 2 inverters in the rear and 1 in the front. Okay, heat sources 11 and 12 come from the stator windings, these copper wires right here called the stator, that goes around the electric motor rotor right here. So I have a cutaway that I've created for the front motor of our Tesla Model Y. The rotor rotates. It rotates because of a rotating magnetic field created in the stator. But we apply high voltage to these stator windings and run a lot of current through them. They get hot. There's a special transmission fluid that an electric pump right here pumps through and runs that transmission fluid over these stator windings to transfer the heat energy out of the stator windings into the transmission fluid. And then we have a special heat exchanger. It looks very much like that chiller that we just looked at, but we have transmission fluid coming in right here and out right here, and that transfers the heat energy from the transmission fluid into coolant that comes in right here and goes out right here. And this just plugs in right here on the side of the drive unit. And there's one, this is the front drive unit. I've got the rear drive unit right over here. There is a heat exchanger for the front drive unit and another one for the rear drive unit to transfer the heat energy from the transmission fluid that it got from the stators into coolant. And then it goes to the chiller where we transfer the heat energy from the coolant into the refrigerant and then into the passenger compartment condenser. So those were heat sources 11 and 12. Okay, the 13th source of heat on Tesla vehicles is actually the cabin evaporator. Now the evaporator, if you recall from our earlier discussion, is normally used to remove heat energy from the passenger compartment, the cabin, for cooling the air, reducing the air temperature. But think about this. If we are trying to add heat energy to the refrigerant that goes to the cabin condenser, if we already have somewhat preheated air in the cabin and the cabin air is on recirculation, meaning we're not pulling in outside air and heating it, we're reheating the inside air. If that air can make a loop and come back through the blower motor and then go through the cabin evaporator, As the air goes through the evaporator, if we allow for some refrigerant to go through the evaporator, the heat energy from the cabin air can be transferred into the refrigerant that then can go to the compressor, that then can raise the refrigerant pressures and temperature that sends it back even hotter to the condenser to heat the air. The next source of heat is another part on the supermanifold. Okay, so right here under the frunk lid on our supermanifold, right on the top is this box right here, and I have another one right here. This is called the liquid-cooled condenser. So here's a liquid-cooled condenser. On the back of it, we have a coolant inlet and outlet. We also have a refrigerant inlet and outlet. So the job of the liquid-cooled condenser is to transfer heat energy from the refrigerant into the coolant. Now that's just the opposite of the chiller. The chiller's job was to transfer heat energy from the coolant into the refrigerant. So these two are opposites of each other. They're similar in size, but the liquid-cooled condenser is larger. The liquid-cooled condenser plugs in on our supermanifold right here in the top, just like this, as you can see right here. Now, most vehicles, including probably the one you are driving, have a condenser out in front of the radiator of the vehicle. And the job of the condenser on that vehicle was to transfer heat energy from the refrigerant to the outside air. Well, this liquid-cooled condenser, instead of losing all of that heat energy to the outside air, we are transferring it into the coolant. And that way we can capture it. We can save that heat energy if we need to. We can store it in the high voltage battery. We can heat the passenger compartment or the power electronics with it. Or if we want to get rid of it, then we already have a radiator. Let's just move some switching valves and run that coolant right out to the radiator, where we can transfer the heat energy in the coolant out to the air in the same manner that a condenser would do. So they've reduced a part in front of the vehicle and replaced it with another part inside the vehicle. So they didn't really reduce the number of parts, but they made it to where we can capture that heat energy rather than just lose it to the air. And so that's a pretty smart way of doing things. And since we already have a radiator whose job is to transfer heat energy from coolant to the air, we don't need two of those. We don't need a condenser that does that and a radiator that does that. We can just use the radiator. So we've talked about a chiller and a condenser. The condenser, liquid-cooled condenser here, is our 14th source of heat. Now, the 15th source of heat is actually the air conditioning compressor, this part right over here. So I have one of these compressors that I've taken apart. So here's a part of it right here. Inside of the air conditioning compressor is a big three-phase stator assembly, much like the drive unit electric motors. We connect high voltage battery positive and negative DC to this. It has its own built-in inverter where it drives a three-phase permanent magnet electric motor, and it turns what's called a scroll compressor. If you look at these photos here, it has a movable scroll and a stationary scroll. And if you watch this video here, you can see the movable scroll doing its thing. Now, this air conditioning compressor stator coil can be a source of heat. So as it operates, it gets hot, just like the transmission or drive unit stators do. Except now, instead of transmission fluid going across it, we have refrigerant going across it. And it transfers the heat from these stator coils into the refrigerant that it's compressing anyway. And by compressing the refrigerant, it increases its temperature by concentrating the heat. and then pumps that to that inside condenser to add heat to the cabin of the vehicle. So the air conditioning compressor itself can be a source of heat. So that's our 15th source of heat on the vehicle, the air conditioning compressor. Now the 16th source of heat is really hard to see. But on this super manifold that we'll look at in a little more detail here in a minute, there are 4 sets of passages that I've color-coded with a permanent marker here. Everything in blue is a low-pressure vapor. Everything in red is a high-pressure vapor. Everything in black is a high-pressure liquid. And anything in green is a low-pressure liquid or vapor. They call it a dual-state refrigerant. Now, if we take some of this high-pressure refrigerant, high-pressure, high-temperature refrigerant, and we run it back into the low-pressure, low-temperature refrigerant side through a little part called a mister, just like a water mister. It just sprays a fine mist. That additional heat energy from the refrigerant will transfer into the low temperature, low pressure refrigerant and add heat energy to it. And that typically only happens at very cold temperatures. It's a way of, it's basically you're short-circuiting the refrigerant loop and adding the additional heat energy from the compressor stator to it. It's a quick way of increasing the temperature of the refrigerant. And that is controlled with a special solenoid over here called the recirculation solenoid that screws into this passage. And there are a bunch of solenoids we'll look at on here to control the direction and flow of refrigerant in this super manifold. But as the 16th source of heat in this heat pump system, that is our final source of heat. And that is under normal operating conditions, which are defined by Tesla as 10 degrees Celsius, 50 degrees Fahrenheit, or above. Now, when the battery temperature drops below the 10 degrees Celsius or 50 degrees Fahrenheit, there are 6 other methods of producing heat that aren't normally used in regular operation of the heat pump system. So let's look at those 6 methods. The number 1 method we've mentioned already, but it has an extra flair to it. So let's come back to our air conditioning compressor stator here. The air conditioning compressor stator normally generates heat as part of normal operation. But in really cold temperatures, as the patent describes, the inverter can control these stator windings in what's called a lossy manner. L-O-S-S-Y, a lossy manner, which means a very inefficient manner. And by being very inefficient, it will produce heat that we don't normally want it to produce. So if something in electronics isn't very efficient, it generally produces heat, a lot of heat, with it. And so by purposely making it run inefficiently or in a lossy manner, we can convert more electrical energy into heat energy in the stator windings to add additional heat to the refrigerant that works its way to the cabin condenser. So this is cold, extra cold temperature. This works clear down to a negative 40 degrees Celsius, which is also negative 40 Fahrenheit. Okay, so that's number 1 of 6 methods in super cold temperatures. The second method is back with our blower motor assembly. The blower motor stator can also be operated in a lossy manner and cause it to generate a lot of extra heat, and that heat energy is transferred into the air and blown across the evaporator and the condenser and into the passenger compartment, the cabin. Okay, the third and fourth methods of generating extra heat, more heat than necessary, is to run the front and rear motor inverters in a lossy manner. And by running those in a lossy manner, they generate more heat than they normally would. and that heat gets transferred into the coolant, that then gets transferred to the chiller, into the refrigerant, to the air conditioning compressor, and then into the cabin heater. The fifth and sixth methods of generating extra heat in really cold temperatures is by using the stator windings of the front and rear drive units. And so we can operate the stators in a lossy manner, much like we did with the air conditioning compressor with the blower motor. We can run the stators in the front and rear motors in a lossy manner, a low power factor manner, and they will generate extra heat. I've done some experimenting while charging and during battery preconditioning. As you can see in this screenshot from an app, the front drive unit was using 3.5 kilowatts of power. The rear drive unit was using 2.5 kilowatts of power with the car stopped, sitting still while preconditioning the battery. And what is that, 6 kilowatts of power? That's very close to the 7.5 kilowatts of PTC heater energy used to create heat on vehicles with a PTC heater. So in really cold temperatures, these 6 methods I just showed you and described to you of using the air conditioning compressor, the blower, the front and rear inverter, and the front and rear stator assemblies, and any combination of those are ways to create extra heat energy, but they do it at a cost, an electrical energy cost, which can be just as high as a PTC air heater or a PTC coolant heater, except these components can generate that heat with the existing parts that are already there. We don't need an extra PTC heater installed on the vehicle. We don't need extra parts installed to generate heat in low temperatures. We just use existing parts and can operate them purposely in a lossy, inefficient manner that creates extra heat. All that extra heat ends up in the refrigerant, compressed by the compressor, heat concentrated, which raises the temperature of the refrigerant, which is then sent to our cabin condenser and air blown through it to keep you warm while you drive down the road. So a pretty amazing system, and quite a wide operating range there, which is quite impressive. This same heat pump system that we're looking at here and describing here for the Model Y is the exact same system on the Model 3, the Model S, and the Model X. They all have the same heat pump system. They all have what appears to be the same supermanifold and air conditioning compressor setup. So it's a modular system that can bolt into multiple vehicles and then just have the existing parts, coolant hoses hooked to it, and then the refrigerant lines transfer into the cabin as we have discussed. Okay, we have just looked at the 16 components of the Tesla heat pump system. Now, as far as overall operation of the system, there is a refrigerant side of things and there is a coolant side of things, and the supermanifold that we took a quick look at has a coolant side and a refrigerant side. And if you go into service mode on many Teslas, you will be able to see the 4 different modes of coolant flow on the vehicle: the series mode, the Series Radiator Bypass mode, the parallel mode, and the ambient air mode. And their relationship to all of these 16 components that we just looked at, along with some additional components that are part of the supermanifold. If you look at this screenshot here from the Tesla service mode, you can see the different solenoids that are part of the refrigerant side of the supermanifold, along with the pressure and temperature sensor readings that are also taken from pressure temperature sensors on the supermanifold. So let's go take a look at the supermanifold in a little more detail next. Okay, here we have the cast aluminum piece of the supermanifold that handles refrigerant distribution. To understand the supermanifold, you must have a good idea of how the refrigerant loop works on a traditional vehicle. So if you look at this photograph here of the refrigerant loop of just about any vehicle on the road, we start with the air conditioning compressor, and it pulls in a low pressure, low temperature vapor and compresses it and concentrates the heat and makes it a high pressure, high temperature vapor. It then is pumped out to the condenser in front of the radiator, where it condenses into a liquid as the air passes through the radiator and it gives off heat. Leaving the condenser, we have a high pressure, high temperature liquid that goes into a receiver dryer where moisture is removed through the use of a desiccant bag, and then it goes to a thermostatic expansion valve, or TXV, on most vehicles. There are other methods out there, but a TXV is pretty common. The thermostatic expansion valve has a small opening where, as the high pressure, high temperature fluid goes through it, it is allowed to expand. And as it expands, its temperature decreases, and now it becomes a low temperature, low pressure liquid that goes into the evaporator. And as cabin air passes through the evaporator, this low temperature, low pressure liquid accepts heat energy from the cabin air and begins to boil. And it boils into a vapor, which is then sent back to the air conditioning compressor. And so we have a complete loop. So there are 4 different states of refrigerant in this loop. Well, the supermanifold cast aluminum piece here has to handle all 4 of those states. So in blue, we have the low pressure vapor return that goes back to the air conditioning compressor. In red, we have the compressed high pressure vapor that leaves the air conditioning compressor. In black, we have the liquid high pressure refrigerant that, after it's gone through the liquid cooled condenser and condensed into a liquid. Then in green, we have the refrigerant that can be inside the evaporator that could be liquid or vapor. Now that translates to the front here. So at the front of this manifold, pretty much everything at the bottom here is the low pressure vapor system. Everything at the top is the high pressure vapor system. We have, as part of the supermanifold here, we have 3 what are called pressure temperature sensors. So here is a temperature sensor that also is a pressure sensor built into one unit. And this is for the suction side, or the low pressure side of the refrigerant system. So that's just going to screw in to the supermanifold right here on the top. Then we have another pressure temperature sensor. This is for the liquid high pressure line, and it screws in right here and measures the pressure and temperature of the high pressure liquid. Then we have another pressure temperature sensor, which is for the high pressure vapor side leaving the compressor. And so that screws in right here. All right, so we've got 3 temperature pressure sensors. So this part protruding out of the manifold portion of the supermanifold is called the receiver dryer and accumulator. And the accumulator's job is to allow any liquid refrigerant to boil off into a vapor before it goes back to the air conditioning compressor, so that we don't break the air conditioning compressor. So that's the job of the accumulator. But there's also a drying portion where we absorb any moisture in the refrigerant through what's called a desiccant bag. The desiccant bag itself is inside of this black cartridge. You may have seen desiccant bags in like a bag of jerky. There's a little pouch in there with these little beads. This has those beads in it. And so this fits in a groove and slides down in to the receiver dryer portion of the supermanifold here. Then it has a plug with 2 O-rings on it, and these O-rings like to get stuck in the snap ring groove that goes right here. So this plug goes in, and then a snap ring goes in on top of it, and then there's a cap that screws on to that plug that keeps dirt from getting into that area where the snap ring is. And so this is a serviceable item. And on Teslas, I think it's every 6 years, the desiccant bag needs to be replaced. On other vehicles, I've seen it as low as 3 years. And the air conditioning compressor is running almost always on these vehicles, not just Teslas, but anybody with a liquid-cooled battery in hot weather. That air conditioning compressor is going to be running to remove heat energy from the battery as you drive or as you charge, and that does it through the air conditioning compressor. Okay, that plug is very difficult to get out. It just shows in the Tesla service information grabbing a pair of pliers and lifting this out. Yeah, good luck. It doesn't come out that easy at all. It's very difficult to get out. All right, now, other parts that are here. We have 3 one-way check valves, 3 check valves. And so let me bring in a check valve here. There are 2 places for check valves right here on the front and 1 place for a check valve on the back. And a check valve is just a spring-loaded plug that prevents refrigerant from going one direction, but allows it to go the other direction. And so we have a cover for the check valve, and then the valve and a spring and a snap ring. And so the check valve is this little rounded piece right here that sits down inside of a plastic housing, and that fits down inside of this hole. There's a spring that sits on top of that check valve and holds it in the closed position, and then there's a plug that comes in on the top with a snap ring that holds it in place. And so there are 3 of these. We have 1 for the evaporator, so that refrigerant can only come from the evaporator and not go backwards into the evaporator through this passage. We have another one for the liquid-cooled condenser, so that it will only go one direction through the liquid-cooled condenser. And then we have another one for the cabin condenser, so that the refrigerant coming from the cabin condenser can only come this direction and not try to go in the outlet side of the condenser pipes. All right, then we have 6 solenoids. 6 solenoids. These solenoids are all identical. They have a plunger with a spring-loaded plunger. It is a normally closed plunger. There's a coil of wire that fits over the top of that plunger, and all of these little normally closed solenoids screw in here on this supermanifold. These solenoids are not serviceable. The check valves are not serviceable. The temperature sensors are, but these solenoid plungers are not. Let me get all 6 of these installed. They all have the same part number on the end of them. They're all the same. There we go. So this is the solenoid mechanical portion, the plunger portion of these solenoids. And these 6 solenoids are, we have one that controls the refrigerant going into the chiller. We have another one that controls the refrigerant going into the evaporator. Another one that controls the refrigerant going into the driver's side of the condenser inside the vehicle. We have another one that controls the refrigerant going into the passenger side of the condenser inside the vehicle. We have another one that controls the refrigerant going through the liquid-cooled condenser. And the last one over here is the one that controls the amount of recirculation refrigerant that goes through that little mister during really cold temperatures to try to boost the heat content of the refrigerant. Each one of these mechanical plungers has an identical coil of wire that fits down over the top of it. They have a seal that fits up inside here to keep moisture out, and those slide down. I'm going to take the seal off because they're really hard to put on and take off. And I need to keep this apart for demonstration for my classes. But this is solenoid coil is just going to sit down. There's a little groove in the supermanifold that it clips over right there, and now it won't come off. And so we have a 4-wire solenoid connector for every or for each of the 6 solenoids. So this one is for the evaporator, this one is for the chiller, this one is for the left cabin condenser, right there. This one is for the right cabin condenser, right there. This one is for our liquid cooled condenser, right there. And the last one is our recirculation solenoid. So now we have 6 solenoids installed to control the amount of refrigerant that goes through these ports. These solenoids can be just on or off, allow a lot of fluid or no fluid. They can also be pulse width modulated to act as a variable orifice. And so those are the solenoids. Now, we have an additional port right here for a larger solenoid. This solenoid here is called the shut-off solenoid valve for the liquid-cooled condenser. And basically, it's a big pressure regulator valve. It's to prevent over-pressurizing of this manifold here. So all 4 of these solenoids, these 4 black solenoids here, are on the high side, high pressure, high temperature vapor side of the refrigerant loop. If we are cooling the passenger compartment, these 2 are off for the driver's side and passenger side of the condenser. This one is off because that's only used in cold temperatures to boost the heat. And so we have the cabin condenser, the liquid-cooled condenser solenoid that controls how much refrigerant goes through the liquid-cooled condenser. If for some reason that gets stuck or fails, all of these could be stuck in the off position, which would cause the high side pressure in the air conditioning system to skyrocket. This will open. It will blow open. I believe it'll blow open. It has a little spring-loaded plunger, and it has a solenoid valve or solenoid coil of copper wire right there that screws on and sits on the top of there to control over pressurizing of the high pressure system. Okay, I'm going to bring in the chiller now. It just plugs in to these 2 holes right here. And we have the chiller inlet at the top from the chiller electronic expansion valve, and the outlet at the bottom that goes over to the receiver dryer. It just has a couple of O-rings and some bolts that hold it in place. AC lube oil on those O-rings. There we go. Goes right in. There is our chiller installed as part of our supermanifold. At the top of the supermanifold, we have 2 holes for the liquid-cooled condenser. So the liquid-cooled condenser is right here. It's going to plug in. Other than the 3 check valves that I did not install, the 2 on the front and the 1 on the back, the refrigerant portion of the supermanifold is assembled. Nothing is torqued or bolted down, but I use this for demonstration in my classes. The 2 holes that you see right here, the red and the blue is the suction side that comes from our air conditioning compressor, and the red is the discharge side from the air conditioning compressor. So those 2 pipes that you see under the frunk over there from the air conditioning compressor, they just plug in right there. So that is the front of our supermanifold. But there's a back portion that is used for coolant Okay, let's look at the coolant part of the super manifold. So there's this big plastic coolant manifold right here. So this manifold has a place for 2 electric water pumps, and then it has 3 places for coolant hose connections. We have one coming from the high voltage battery, one coming from the high voltage powertrain, and one going to the high voltage battery. And then on the front here, we have the coolant connections to the chiller, coolant connections to the liquid cooled condenser, and then 3 more coolant connections, one to the radiator down the bottom center here, one from the radiator, and one from the high voltage powertrain. Okay, so on the back side here, I'm going to get our coolant pumps. Here they are. There's 2 of them. There's one coolant pump for the battery, which is this one, and one coolant pump for the high voltage powertrain. These are both the same part number. These are three phase 16 volt motors. They max out at 6,000 RPM and draw 15 amps apiece when they're at that speed. The battery coolant pump goes at the bottom down here, and so we will plug that in. It matters its orientation. I think it only goes one way, but these pumps are serviceable. Put the screws in it to keep them from falling out. And then we have the powertrain pump also, and it only bolts in one direction. Okay, so now we've got our 2 coolant pumps installed. Powertrain pump at the top, high voltage battery pump at the bottom. Now there's another component that goes here, and it's called the octovalve. The octovalve, octo meaning 8. This is an 8-way coolant switching valve. And if you look right here in this plastic manifold, there are 8 ports right here. These ports can be connected together up and down like this, or even side to side, depending on the 5 different positions of the octovalve. It has 5 positions, but only 4 of them are used. So there is an electric motor and a position sensor on the bottom of the octovalve. It just has a big, like a canister that it spins inside, or that it rotates, it doesn't spin, inside to give us the different positions for the 4 different coolant modes. Actually, there's 5 coolant modes if you count off on the Tesla vehicles. So we'll get that sensor and motor screwed down here. There we go. Okay, if you look at these drawings of the 4 different modes of operation, the first mode, which is full counterclockwise rotation of the octovalve as viewed from underneath the octovalve, we connect port 5 to port 1, so the coolant goes straight up. We connect port 2 to port 6, so the coolant comes down. And then we connect port 4 to port 3, so the coolant goes in a loop from 4 to 3, and then also from 7 to 8. So that is one of the 4 octovalve usable positions. All right, now the next octovalve position, we just move the octovalve clockwise 1 position. And by doing that, we switch to this Series Radiator Bypass position. The first position, by the way, was called parallel mode. So now we're doing the Series Radiator Bypass. We connect port 5 to port 1, port 2 to port 3, port 6 and 7 are connected together, and then we connect port 4 to port 8 and allow coolant to flow there. All right, then the next position, we just slide everything over 1, is called Ambient Source. And as you can see, we connect port 2 to port 1, port 5 to port 6, port 7 to port 3, and port 4 to port 8. So there's our third mode out of 4. And our fourth mode is called series mode. And in series mode, the coolant just goes straight up or down. So we connect port 5 to port 1, port 2 to port 6, port 7 to port 3, and then port 4 to port 8. So these are the 4 different operational modes of the octovalve. We are switching coolant on 8 different passages at once with this octovalve assembly. So the octovalve bolts in right here. The octovalve is serviceable. You can replace the octovalve if necessary. Okay. So now we have assembled the back half of the plastic portion of the supermanifold that controls the flow of coolant in the system. And what's beautiful about this design is that instead of having a pump that's remotely mounted with hoses that would connect to it and then hook to something else, they got rid of the hoses and just moved the pump into here. The same thing with the octovalve here. This is really 2 4-way switching valves that would have been remotely mounted somewhere else on somebody else's vehicle, including the older Tesla Model S and X, and then they moved it to this manifold, got rid of the hoses and hose clamps, and it all became one part of this super manifold assembly. So they were able to reduce the number of parts on the vehicle. Now, this plastic portion bolts to the aluminum portion here. So I'm going to lay the aluminum portion down, put the plastic portion in its proper location here, just like that. There are some seals that are underneath it that allows the sealing of the aluminum chiller to the plastic portion of the super manifold here. There's also seals where it goes from the liquid cooled condenser to the plastic. It has to seal and have no coolant leaks there. This plastic portion and the aluminum portion are not serviceable. You're to replace the entire super manifold assembly if either one of these get broken. Okay, now we have the entire super manifold assembled. The only other thing that we could bolt to it would be the coolant reservoir. And what's neat about this super manifold is it's universal. This can bolt into a Model Y, it can bolt into a Model 3. I believe it can bolt into the Model S and X also. But you just change the coolant reservoir. So this reservoir plugs in right here, and there's a bolt from the other side that holds it in place. There's 2 of these, and it seems like the other one is on the back. Let me see. Yes, it is, right there. Okay, there is the complete super manifold. We control the flow and direction and volume of refrigerant in the cast aluminum piece, and the same thing on the back in the plastic, except for the flow of coolant. There is a set of the 5 pipes right here that's going to bolt in to the back of the super manifold right here and go into the cabin, as we saw under the frunk lid of our Model Y over there. A series of 5 pipes. And then, of course, there is a wiring harness that plugs into all of those solenoids and pressure temperature sensors and the the pumps and the octovalve and the fluid level sensor and so on. This is a very impressive system, in my opinion. There's a lot of heat pump systems out there. If you look under the hood of our Kia Niro over here, it has a heat pump with a PTC air heater. It doesn't have the operational range that this heat pump does, but it isn't as refined. It has aluminum pipes going everywhere. It has a bank of solenoids up underneath the hood, as you can see here on the passenger side inner fender. It's just pipes and pipes and pipes, and I think it's an evolutionary process where Tesla, I think, has really thought this system out well and brought everything into one modular piece that can be moved from vehicle to vehicle or installed from vehicle to vehicle. All right, so wrapping up this video, it's been a long video. The big advantage to a heat pump system for cabin heating, if you live somewhere where you use cabin heating, is it only uses heat energy from the air conditioning compressor under most operating conditions. The Teslas I've driven that have heat pumps are very impressive in very cold weather, and I have no complaints at all with them. Only uses a small amount of electrical energy unless the temperatures are really, really cold. And in that case, then it uses existing parts to create heat rather than additional bolt-on parts like some other vehicle manufacturers have. So, if you're in a market for an electric vehicle, I would recommend you seriously consider one with a heat pump. All heat pumps are not the same. Do your homework, do some research, find out customer reviews. Tesla has had some problems with this heat pump when it first came out, with no heat at all occurring, and they figured out that there was a solenoid that was not bleeding off pressure at a certain time when it should have been, and they've released a software update to fix that. All right, well, thank you for watching. As always, if you think you benefited from this video, please feel free to donate to the Weber State Automotive Department. There's a link in the video text shown below this video here. Until next time, have a good day.